Halogenoalkanes. A halogenoalkane is an alkane in which one or more of the hydrogen atoms have been replaced by a halogen atom. So for example here, we have chloromethane, bromomethane, and iodomethane. So as you can see, a hydrogen has been substituted for a chlorine group, a bromine group, and an iodine. So halogenoalkanes can be primary, secondary, or tertiary, depending on the amount of methyl groups they have. So here we see one bromobutane. As you can see, there is one methyl group, so therefore it's a primary halogenoalkane. Here is two bromobutane. This one is a secondary because it's got two methyl groups, as shown here. So, as shown here and here, it's two methyl groups, making it a secondary. And then we have 2-bromo-2-methyl propane, which is a tertiary because it has 1, 2, 3 methyl groups. Physical properties. So they have permanent dipole, and London forces between their molecules, which is their intermolecular forces. But they have no hydrogen bonding, as they are not directly bonded. No hydrogen is directly bonded to the O. Therefore, it's not going to be as positive enough as it needs. So, for example, let's take chloromethane. And then we'll take another molecule, as we're showing the intermolecular forces. So we're going to have this dipole, this permanent dipole force, which means that we're going to get a delta positive charge here, a delta negative charge here, and that will be the same for this molecule. I'll cover that more in intermolecular forces, and therefore we're going to get this permanent dipole force going between these molecules from this delta negative to this delta positive here, but no hydrogen bonding, which is very important because we don't have hydrogen bonded to either an N, an O, or an F. Those are the three: O, N, or an F. Then it would exhibit hydrogen bonding. A little bit about the boiling points here. So despite the electronegativity difference, the London forces are more important in this instance. So therefore an increased chain length will mean an increased boiling point, because if you've got more carbons, you'll have more electrons, which means you'll have stronger London forces, therefore there'll be more energy required to break them. Down the group you'll have an increased boiling point also, because there's more electrons, stronger London forces, more energy required, same way. And decrease in boiling point as you go from primary, secondary to tertiary, because there's more acyl groups. So even if you had the same amount of electrons, their shape in this instant determines the London forces, because they have more branching, therefore they won't pack as efficiently. So they have weaker forces in between if they've got more methyl groups. Solubility-wise, they are not polar enough to be soluble, so therefore they are immiscible in water, and they just operate well in organic solvents instead. And that's obvious. That's likely due to the fact of the hydrogen bonding, because other organic molecules, such as alcohols, will, because they're able to hydrogen bond with the water. That's only for short chain. Preparation of halogenoalkanes. So this is a bit similar to the reactions of alcohols with each halogen. So if you want to look back on that video, it might be helpful too, but this will run through all of them. So let's start with chloroalkanes. The first way to make them is with PCl5. So let's take green. So that's a PCl5, and this is not very economical. PCl5 is very expensive and has to be dry, so you don't produce HCl. So because if PCl5 reacts with water, it will make HCl. So in this instance, let's just take an alcohol here. A lot of these will be from alcohols. So here we have propantuol, and we can react it with PCl5, and we get the OH group substituted for our chloride group. Oops. And then also we will have produced POCl3, and more importantly though, we will have HCl, which allows this to be shown. So this will show us steamy fumes of HCl, and then also if you tested this with litmus paper, it would react as an acid, because obviously you've got hydrogen chloride. So the second way of making chloroalkanes is by hydrogen chloride, which is produced in situ, so it's slightly safer than the previous one, whereas because it just came off, whereas this one is produced in situ, so it's a bit better. So this is how we form a HCl first of all. So we get so we react KCl and sulfuric acid, which is concentrated. Remember, it has to be concentrated, otherwise it won't work. And this means it's safer because we're getting this produced in situ. So let's take, once again, our propantuol. Just a quick sketch, so don't judge my drawing skills. So then we can add this HCl, which we've made here. And similar to previous example, we'll get that group substituted on. And in this case, we will only produce water. So that shows how it's a lot safer. Moving on to bromoalkanes. So there's two ways of bromoalkanes being made also. So the first way we're going to talk about is bromine and moist red phosphorus. So this is made in situ by this equation here. So we get our phosphorus and the bromine, and we can make our PBr3. Let's just go black. So let's take, once again, you get the idea, there's hydrogens there. So then we're going to add PBr3, and the product of this we're going to get is similar substituted group for the OH. We're going to get our bromo group here, and we're also going to produce H3PO3. So the second way to make bromoalkanes is by hydrogen bromide, which is produced in the vessel from sodium bromide and 50% concentrated sulfuric acid. So again, take our propan-2-ol, and we just react it with a hydrogen bromide. This is similar to the hydrogen chloride, which is the second way of making our chloroalkane. And it's going to form our product, which would be bromoalkane and water, additionally. There we go. Sorry. So hydroalkanes. So unlike the other two, there is only one way to produce them, because it can't be done with the sulfuric acid and the HCl and the HBr, because it would because the iodide has a large ionic radius, so it's easy to lose the electrons, because it's a strong reducing agent, so it would not work. So if we just go with Pi3, let's take our propan-2-ol, and then we'll take our Pi3. Oh, oops, I forgot that's produced in situ. So that's produced in situ, similar to the PCl5 and the PBr reaction. That's going to make product, and it's also going to make two things, Hi and then additionally POI. So just an overview of the preparation. So if we just take our alcohol here, we can make it into a chloroalkane via PCl with dry conditions, hydrogen chloride produced in, or hydrogen chloride produced in situ. We can make it a bromoalkane by bromine and moist red phosphorus, or hydrogen bromide produced in situ. And finally, we can make it an iodalkane just through iodine and red phosphorus. So now on to the reactions of halogenoalkanes. There are quite a lot of reactions, so we'll just break it down and hopefully you'll be able to understand. Nucleophilic substitution is what halogenoalkanes usually go through, so that halogen group being substituted off. So let's break down nucleophilic substitution first. So a nucleophile is a species with a lone pair of electrons, so it is attracted to a nucleus, which is obviously protons. So examples of nucleophiles include water and hydroxide ions, but they can be of varying strengths. So for example, water is a weak one, whereas a hydroxide ion is a much stronger nucleophile. Substitution is where an atom or group of atoms is substituted by another. So say a chlorine group being substituted for something else. And then there are two types you need to know for halogenoalkanes. So we've got an SN1 mechanism, nucleophilic substitution 1, whereas one species involved in the slow step, and there's another one, SN2, where two species are involved in the slow step. And you learn a bit more why in kinetics. So let's just go through a general nucleophilic substitution reaction, with just a random one, because maybe that'll help us understand a bit better all the rest of them, because you don't have to remember every single one of them actually, but if you just sort of remember the way to do it, you can apply your knowledge from there. So if we just take let's just put that in Cl group there. Maybe that in a different colour, just to show. So it's a Cl group there. Sorry, there is a Cl group there. So if we just take this as our nucleophile to represent it, and remember it's going to have a lone pair. It doesn't always have to have a lone pair, but it often has a lone pair because it needs them to be able to attract to there. So we'll usually get this lone pair move into this carbon here. So there's a dipole here, making this delta positive, and therefore we will get this bond popped as such, and that will be substituted on to form our product, which has got rid of this Cl group, for example, and replaced it with our nucleophile. So the trend in reactivity of different halogens in halogenoalkanes. So effectively here we're talking about the strength of the CX bond, X being the halogen. So down the group, substitution occurs more easily. So for example, if we take CCl here, CBr and CI, there is a downwards trend because there is a larger radius and there's more shielding, but the increasing proton number is outweighed. So overall, this means the electron pair is held less strongly than it would be. So therefore, a Ci will be most readily substituted. We can test for this by timing how long it takes to form precipitate, but you don't make sure all primary and make sure they all be the same. So you just be changing this factor here. When they're mixed with silver nitrate and ethanol and water, because you can form precipitate from that reaction, and the hydroalkane will be fastest, as it is the most reactive, because the electron pair is held less strongly. So the trend in the reactivity of primary, secondary, and tertiary halogenoalkanes for substitution is different. So it goes tertiary, secondary, primary, because tertiary carbocations are more stable due to the weakly electron donating effect of methyl groups, which is also called the inductive effect. They undergo the SN1 reaction due to steric hindrance from these methyl groups. So let's move on to the actual reactions now. Let's start with aqueous alkali. This is a good example of both SN1 mechanisms and SN2 mechanisms. So let's start with an SN1 mechanism. So this is for tertiary alkanes only. You've got to make sure you get that right. It's only for tertiary halogenoalkanes. That means it's an SN1 mechanism. So it's a two-step mechanism with only one molecule involved in the slow step of the reaction. So, for example, let's take a tertiary halogenoalkane. As you can see, we have 3 methyl groups attached and our halogen here. So we're going to have this dipole set up here, and this can move into our slow step, which only involves one molecule here, and we can then move on to this having a full positive charge, because it becomes a stable carbocation, because as these groups are electron donating, they increase the electron density here, and that makes it a more stable carbocation. It stabilizes the positive charge. So we have our nucleophile, which is a hydroxide ion from the aqueous alkali, and that is going to attack the carbocation. This is going to be our fast step of the reaction. And we keep doing that. And then you can end up with our product where the OH group has been added on or substituted on here. So unlike our tertiary halogenoalkanes, primary halogenoalkanes undergo an SN2 mechanism. So this is a one-step mechanism with two species involved in the slow step. So in this instance, we can just take any primary halogenoalkane, and in this instance we're still going to get our dipole, and instead of having one species in the slow step, in this case we're going to have two. So this is a one-step mechanism, so we can already have our hydroxide nucleophile able to attack, whereas in the previous one it was not able to attack in the first stage it was. So these can attack here. This pops this bond, and we're going to have a transition state which can't be caught, and it doesn't exist as such, but it does go through this stage to sort of push this Cl group out. So we do it in brackets because it's a transition stage, and what we can do is we sort of highlight this bit there. So what we can do is we can bring our OH group and represent this by a dotted line as it pushes out on the other side our halogen. And this is going to be negatively charged. Another thing to note is that this angle here is always 180 degrees. Therefore, finally, we'll end up with our substituted product, an OH group. So next up is the reaction with ammonia, which is a little bit different. It's an SN2 reaction. So we're just going to look at an SN2 reaction. So it produces a primary amine, firstly, and it's done by adding alcoholic ammonia, and you heat it in a sealed tube. So as you can see here, we add R representing our alkyl group, and X representing our halogen group, add ammonia, and you can see we've substituted it in. So let's go through the mechanism now. So first of all, what's going to happen is, let's just take very simple halogenoalkane, and we're going to get our nucleophile, in this situation our ammonia, and its lone pair is going to go onto this carbon here, which obviously again has our dipole, and this is going to pop this bond, making us have here the nucleophile attaching. So here we're actually going to get a positive charge, and we're going to have a Br minus here, because that's showing that we've made a salt here, actually. So, because we've still got this positive charge, it's unstable still. So, it goes through another stage in the reaction. And in this case, we've got, as you can see here, we've got 2 here. So I'll go on to kinetics and talk about how you can determine mechanisms from rate equations and equations, but you have to worry about that in a moment. So we're actually going to get another ammonia attacking instead here with its lone pair, and that's going to pop this bond to move into here, and therefore I'll just run out of space. So we're going to get here. Oops. This product. Now, the problem with this, if you've spotted it already, then maybe you'll know, but we're also going to have a lone pair on here. So as well as getting our other product, which is going to be a salt, as this has broken off with the, oh sorry, oops, it's Br we were using, with this. But this is also going to go on to react because it has its lone pair. Therefore, we're going to keep reacting with this until we reach an ammonium salt, which is quaternary. Therefore, it won't have any more lone pairs. But this will be covered more in amines. So another reaction you need to know is the reaction with water, which is a hydrolysis reaction. H2O acts as a nucleophile, which is weak. You first need to dissolve the halogenoalkane in ethanol, then add water and warm it. So if we start this reaction, let's just take, again, a simple halogenoalkane. We have our dipole. Then we can add in our water molecule, acting as our nucleophile in this instance because of its lone pair. And it can attack here, pop this bond. As you can see, they follow quite a similar pattern. And we can show that this has formed here our water on it. However, if you've noticed, similar to the ammonia one, this is going to have a positive charge. Therefore, we're going to get another water molecule reacting with it. So it's going to attack this hydrogen, and it's going to pop here, and then we're going to form an alcohol. And then also we'll get HCl. So if you've noticed, then this will be our final product. Moving on to the reaction with potassium cyanide. This produces a nitrile, where the cyanide ion acts as a nucleophile in this case, but also a key thing here is that it increases the length of the carbon chain, which is important if you need to be able to do that. So, in this case, we can take KCN and our halogenoalkane and make our nitrile. So, let's just take oops, it's got a bit askew. Sorry, my mouth isn't the best. Just going to take our halogenoalkane, got our dipole, delta positive, delta negative. Then we've got our cyanide ion. And this is going to attack here, pop this bond, and it's going to make us our nitrile. But as you can see here, as we've added our C, we've increased our carbon length. And another thing to note is this is going to be a triple bond to here. Then we'll also produce K plus Br minus salt from the, so this will be KCN. Next, with ethanoic potassium hydroxide, so this is going to produce an alkene where the hydroxide ion acts as a base. So in this case, it's actually an elimination reaction. So, and for this to work, you might want to heat under reflux. So, for example, let's take a bit more complex. Not too complex, obviously, but a bit longer halogenoalkane. And what we can do here in this reaction, we can make ourselves an alkene with this double bond here being the functional group. And it's important that it's ethanoic potassium hydroxide 2. To remember that, because otherwise we'd make an alcohol, because it would act as a base and it would remove H+. And then we're also going to hear HBr. Testing for halide ions. So this has to be done in solution, and the way you do it is you add nitric acid, which acidifies the solution and reacts with any other ions that may change the precipitate. You add silver nitrate, and with fluoride you'll get no precipitate, you don't have to worry about that. With chloride ions you'll get a white precipitate formed. Bromide you'll get a pale cream, and an iodide you'll get a pale yellow. So these are quite hard to actually distinguish when you're actually observing them in lab, but there is a slight difference if you can see between, and if you can get a white tile it is a lot easier, or being able to compare between them when you see them side by side you can just see little differences, but especially bromide and iodide, they're quite hard to distinguish between each other. A way of getting by this is to confirm precipitates. So this is done by adding ammonia. So effectively what happens here, because we get our precipitate being formed, which this is our white precipitate here, because we've reacted it with silver nitrate and will form AgCl. So for example, we've got you add dilute ammonia and you add conc ammonia in different samples. So in both dilute and concentrated, our chloride will dissolve to a colourless solution. With dilute ammonia, bromide won't, but it will with concentrated, and with both, with iodide, they will both be insoluble. So this is a good way to test between